Imagine for a moment that every message you send, every password you type, every digital transaction you make could be intercepted and read by anyone with the right tools. Your bank account details, your personal conversations, your most private thoughts shared online, all completely exposed to prying eyes. This terrifying scenario would be our reality today if not for the brilliant mind of a wild-haired physicist who revolutionized our understanding of the universe over a century ago. Albert Einstein. The name alone conjures images of genius, relativity, and that famous equation E equals mc squared. But what many people don't realize is that Einstein's groundbreaking work in quantum physics, the very field he famously struggled to accept, has become the foundation for the most secure communication systems protecting our digital world today. The man who once declared that God does not play dice with the universe inadvertently provided us with the ultimate dice game, one that makes our data virtually unbreakable. Every time you make an online purchase, send a confidential email, or access your banking app, you're relying on quantum cryptography principles that Einstein helped establish. His 1905 work on the photoelectric effect, which earned him the Nobel Prize, revealed that light behaves as discrete packets of energy called photons. This discovery didn't just change physics, it laid the groundwork for quantum key distribution, a technology that can detect any attempt at eavesdropping with mathematical certainty. But here's where the story becomes truly fascinating. Einstein himself was deeply uncomfortable with the implications of quantum mechanics. He spent the latter part of his career trying to prove that quantum theory was incomplete, famously engaging in heated debates with Niels Bohr about the fundamental nature of reality. Einstein believed in what he called local realism, the idea that objects have definite properties regardless of observation, and that nothing can influence something else faster than the speed of light. In 1935, Einstein, along with colleagues Podolsky and Rosen, published a thought experiment that he believed would expose the absurdity of quantum mechanics. They described a phenomenon where two particles could be entangled, mysteriously connected in such a way that measuring one instantly affects the other, regardless of the distance between them. Einstein mockingly called this spooky action at a distance and argued it proved quantum theory was fundamentally flawed. Little did Einstein know that his spooky action at a distance would become the cornerstone of modern quantum cryptography. Today, quantum entanglement, the very phenomenon he tried to disprove, is being used to create communication channels so secure that any attempt to intercept them immediately reveals itself. Major tech companies and governments worldwide are investing billions of dollars in quantum communication networks based on principles Einstein reluctantly helped establish. The irony is profound. The man who sought to restore certainty and predictability to physics gave us the tools for ultimate uncertainty in cryptography, and that uncertainty is exactly what keeps our digital secrets safe. Einstein's quantum legacy protects everything from state secrets to your grandmother's recipe shared over email. His reluctant contributions to quantum theory now guard against cyber attacks, industrial espionage, and digital surveillance in ways he never could have imagined. Today, as we stand on the brink of the quantum computing revolution, Einstein's theories are more relevant than ever. The same quantum principles he questioned are now our best defense against the quantum computers that threaten to break traditional encryption methods. It's a race between quantum code makers and quantum code breakers, and Einstein's fingerprints are all over both sides of this digital arms race. This quantum arms race didn't begin in some high-tech laboratory or government facility. It started in 1905 in the cluttered office of a young patent clerk in Bern, Switzerland, who was about to shatter our understanding of light itself. Einstein's explanation of the photoelectric effect, the phenomenon where light knocks electrons out of metal surfaces, would become the foundation stone upon which our entire digital security infrastructure now rests. Before Einstein, scientists believed light was purely a wave, flowing continuously like ripples on water. But Einstein proposed something revolutionary. Light comes in discrete, indivisible packets called photons. Each photon carries a specific amount of energy, and when it hits an electron, it either has enough energy to knock it free or it doesn't. There's no in between. This all or nothing principle seemed almost absurdly simple, yet it explained why shining brighter light on a metal surface produces more electrons, but not more energetic ones. Only increasing the frequency, the color, of the light could do that. Fast forward to today, and this seemingly abstract concept has become the backbone of quantum cryptography. In quantum key distribution systems, individual photons carry the digital keys that protect our most sensitive information. Just as Einstein showed that you can't have half a photon, modern quantum cryptographers exploit the fact that you can't copy or measure a quantum state without disturbing it. When Alice wants to send Bob a secret message, she encodes her encryption key into the quantum properties of individual photons, their polarization, phase, or spin. Here's where Einstein's discovery becomes your digital bodyguard. If an eavesdropper named Eve tries to intercept these photons to steal the key, she must measure them. But the act of measurement fundamentally alters the quantum state of the photons. It's like trying to read a message written in disappearing ink that vanishes the moment you look at it. When Bob receives the photons and compares his measurements with Alice's, any discrepancies immediately reveal Eve's presence. The very attempt to spy destroys the information being spied upon. This isn't just theoretical elegance, it's practical magic happening right now. In 2016, China launched the world's first quantum communication satellite, nicknamed Micius, which uses Einstein's photons to create unhackable communication links between ground stations separated by thousands of kilometers. Banks in Tokyo are using quantum key distribution to protect financial transactions. Government agencies across Europe have built quantum communication networks that would make even the most sophisticated hackers throw up their hands in defeat. But perhaps the most beautiful irony is how Einstein's reluctant quantum legacy solves a problem he never could have anticipated: the looming threat of quantum computers themselves. Traditional encryption methods that protect your credit card information and personal data rely on mathematical problems that would take conventional computers millions of years to solve. A sufficiently powerful quantum computer could crack these codes in hours or days, rendering most of our current digital security obsolete overnight. Yet Einstein's photons offer us salvation. Quantum key distribution doesn't rely on mathematical complexity. It relies on the fundamental laws of physics that Einstein helped discover. Even if someone builds a quantum computer capable of breaking every traditional encryption method, they still can't violate the quantum mechanical principles that make photon-based communication inherently secure. It's as if Einstein, despite his discomfort with quantum uncertainty, provided us with an unbreakable shield just when we need it most. The patent clerk who revolutionized our understanding of light never imagined that his photons would one day carry the digital DNA of our civilization, our financial records, medical data, personal communications, and state secrets. Every quantum encrypted message sent today is a testament to Einstein's genius, proof that fundamental scientific discoveries have a way of finding applications far beyond their original scope. But Einstein's quantum legacy didn't stop with photons. In fact, his most famous criticism of quantum mechanics, what he dismissively called spooky action at a distance, has become perhaps the most powerful weapon in our cybersecurity arsenal. Einstein was referring to quantum entanglement, a phenomenon so bizarre that it troubled him for the rest of his life. Yet today, it forms the beating heart of our most advanced quantum communication systems. Picture this. Two particles become entangled, creating an invisible quantum bond that persists no matter how far apart they travel. Measure one particle and instantly, faster than light could travel between them. You know the state of its partner. Einstein, along with colleagues Podolsky and Rosen, argued in 1935 that this violated the fundamental principle that nothing can influence distant events instantaneously. They insisted there must be hidden variables, secret information that predetermined each particle's behavior, making the correlation only appear instantaneous. For decades, this remained a philosophical debate among physicists. But in 1964, John Bell devised a mathematical test that could distinguish between Einstein's hidden variables and true quantum entanglement. When experiments finally put Bell's test to work in the 1970s and 80s, the results were unambiguous. Einstein was wrong about hidden variables, but his spooky action was gloriously, mysteriously real. Today, this same spooky action that Einstein couldn't accept has evolved into quantum teleportation, not the science fiction kind where Captain Kirk materializes on alien planets, but something far more subtle and infinitely more useful. Quantum teleportation allows us to transfer the complete quantum state of one particle to another, instantly and perfectly, across any distance. The original particle's state is destroyed in the process, ensuring that no copies exist, a built-in security feature that would make any spy agency weep with envy. Here's how Einstein's rejected phenomenon now guards your digital life. Imagine Alice wants to send Bob not just an encryption key, but the key generation process itself. She creates pairs of entangled photons, keeping one from each pair and sending the others to Bob across a quantum channel. When Alice performs measurements on her photons, Bob's corresponding photons instantly reflect those measurements, creating a shared sequence of truly random numbers that no computer, quantum or classical, could predict or reproduce. This isn't just theoretical elegance, it's happening in the real world right now. The European Quantum Internet Alliance is building a continent-spanning network of quantum-entangled nodes that will make intercepting communications not just difficult, but physically impossible. In China, researchers have achieved quantum teleportation over distances exceeding 1,400 kilometers using satellites, creating communication links that would make even Einstein's skeptical ghost take notice. But perhaps the most delicious irony is how entanglement solves the authentication problem that plagued early quantum cryptography. How do you know that the person claiming to be Bob is actually Bob and not Eve masquerading as him? Traditional methods rely on shared secrets or digital certificates that can be forged or stolen. Quantum entanglement offers something unprecedented: identity verification based on the fundamental structure of reality itself. When Alice and Bob share entangled particles, they share something that cannot be duplicated, transferred, or faked. The correlations between their measurements follow patterns that only genuine entanglement can produce. Any attempt by an imposter to fake these correlations would require them to violate the laws of physics. Specifically, Bell's inequalities that proved Einstein wrong. In essence, every quantum authenticated communication is verified by the universe itself. The patent clerk who spent his later years trying to disprove quantum entanglement never imagined that his spooky action would become the foundation of unhackable authentication systems. Today, every entangled photon pair used in quantum networks carries a piece of Einstein's intellectual DNA. his rigorous demand for physical reality, even as that reality proved far stranger than he was willing to accept. As we stand on the brink of the quantum internet age, Einstein's reluctant quantum children, photons and entanglement, are preparing to revolutionize not just how we secure information, but how we think about communication itself.